Hello and welcome to today's Smart Safety Connection Seminar. My name is Jun-Sun Huang and I am a Safety in Transportation Fellow for Safety 21, US DOT University Transportation Center. The Smart Safety Connection Seminar series is sponsored by Safety 21 as an opportunity for faculty to showcase their current transportation project. It is also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster future interdisciplinary collaboration. Please note today's session is being recorded and all participants' microphones are muted. If you are joining us online, please send your questions through the chat, or if you are here with us in person, feel free to raise your hand. You do not need to wait until the end of the presentation to ask your questions. You are welcome to ask them throughout. Now, I'd like to introduce today's speaker. Dr. Christoph Mertz received his PhD in physics from Arizona State University. In more than 25 years at CMU, he developed surround sensing and object detection systems for intelligent vehicles and search and rescue robots. He worked on projects sponsored by ARL, DOT, FDA, PANDOT, NIJ, DARPA, NSF, DoD, and several companies. His current research focus is on autonomous off-road driving and developing nighttime perception. Besides his full-time position at CMU, he has been co-founder and chief scientist at ROADWork. The startup has been acquired by Michelin, where he continues his part-time position as a consultant.
Thank you. I just realized some of you have not been born when I started here.
You're not alone in that, by the way.
But that's fine. So I hope you can bring some wisdom here. You might have all heard about this phrase long tail, right? Concerning AI, machine learning. That's basically where rare events, rare objects, and so on. And in transportation, which, UTC has it in its name, one of the rare things which you see while you drive around is work zones. And it is part of a long tail, but it's actually a very dangerous long tail. That's why I have this sort of dinosaur tail up there, just so that future people can see that I used AI to create that. And yeah, that's what they did at that time. So here's all these people who contribute to that. Most importantly, Anurag, which is over there. If you ask me too detailed questions, I'll refer to you. That's what you do, right? That's why you have students. So safe driving cars, they struggle with road work. You might have heard about some of these things I show you, right? So, and actually people can use it against them, right? By putting this cone in there and then, I have to stop. Right? So it's a clever way to stop them, right? Because you outsmart them. It's still good to know that humans are smarter than robots. So this is a case where it thinks there's a work zone right in front of it and stops, but it's not. Another one is here. This is actually, you might notice this. It's very cool. You might almost see it looking out the window here. You see there's this sign, road closed to traffic, right? To through traffic. But if you look a little bit closer, there is no road. There's no road behind it, right? And so what apparently happened, I mean, if you know around here, they closed this lane here, right? And had it closed up. And then they were done with it and took the sign and put it on the sidewalk. Right? And there it is. And you can see that even, when you looked at it the first time, you probably thought there's actually closed road. You click close it and said, oh yeah, that's something wrong. How can an autonomous vehicle? I mean, you really have to do lots of reasoning. But you see that sometimes, like those signs, and it might also be like they're transporting these signs in the back of their truck. You see, so there's deceptive road signs. Another, you might have seen this in the news. So there's this construction zone, and they put these things in there, but there's this big gap in between, and the autonomous car didn't see it and went right through it, right? Now, like if you're a little bit too sleepy, you might actually, a human might also, but it doesn't get into the news like them. But of course, it was all over the news. So this might be sort of struggle understanding what drivable space is. And there's something also sometimes very tragic ones. Here's actually a fatal accident, which happened just in March this year. It was in China, autonomous vehicle there, and it was also in a work zone. Right? So that certainly is very dangerous, those work zones. So object detection is one of the simplest things, fundamental things in computer vision. And it is not enough if you have a scene here to detect all the objects. For example, here are the stop signs. If I just detect the stop signs, I miss that they're actually being held by a person. And as we all know, that means that's a different meaning of the stop sign. Because usually there's a stop sign, you stop, and then you go if it's free. Here it means stop and stay stop till I turn it around. It's very different, right? So we also need to understand that the worker is holding the sign, and also this car, you see, it's actually driving on the wrong side. This is not in Great Britain, this is in the United States, and you are allowed, and sometimes you have to drive on the wrong side, right? So, so you have to understand that at some point they will turn it around, but it's a person turning around, so you don't have to can't be 100% safe, sure that once it's so slow that you can just go, you still have to see that, oh, this car is still driving in my lane, and you wait a little bit and then you can go. So you have the first thing is to just recognize the object, okay? Then the next thing is that you have to observe the details, like in local context. So you read it and you see that there's a person there, and then you still have to analyze the whole scene, all the different parts which come together, and then you can drive. So here again, here's another example. So this is just one of the images. So this is now all labeled. So these are the objects, right? All the objects of semantic. Then the local details, like here, keep right, road closed, left reserved. Sometimes it's written on there, so you can recognize it. Sometimes it's like you have to interpret the signs on them, and then analyze it globally. What it all means, so that it's okay. So like this left lane here is closed, so I'm not going to be able to turn left here, and the right lane is closed, so I just have to drive here. And even here, here's a sign on the sidewalk, so maybe the pedestrians are going to be somewhere else. And then here's the path now the car has to go through. So what did we do? So our big contribution to this topic is we created a data set, okay? So, which we call the ROADWork data set. And here are a couple examples. So these are the images, and then we labeled them. We first labeled the individual objects, including the mask of the objects. Then the local context, like this is left arrow, keep right, right Then we also put a text, an annotation of a description of the whole scene. And we have the path that the vehicle drove through. So, now you might notice the path there, that's, we didn't annotate that. It's the actual path that the vehicle drove through. And later on, I will tell you how we got that path from the images. Actually, we got it from the video, but so these are just the examples of the labeling we did for this. And so we get over 5,000 unique work zones. Now, you might say this is 5,000. That's not as many as other data sets which have millions of pictures, but was a huge amount of work. And as I said, it's a long tail. So we got it from all over the United States. So here's a different, and we got this from the robotics data set. So these are different cities in the United States. And then one example here is you also see how where in the city it was. So it's also distributed there. So 19 different US cities, and we discovered images from around the world. We had a little bit over 4,000 videos from that, so it's like 30-second videos. That's how we then also got the paths. And almost 10,000 annotated keyframes. So here you see the statistics about the different signs, different objects, and the ones which are there in red, like drums, TTT sign, vertical panel, and so on. Those are the objects which we were not able to find in any other data set, right? So there's the mapillary, there's the new scenes, and so on. They don't have those which are in red. What many have are cones, which are fairly common. Others, like worker or police officer, they are people, so they have people, but not necessarily say this is a police officer or there's a worker. So, so there's something which are completely new, or with respect to other data sets. And of the temporary traffic control signs, like here, there's 360 different kinds, right? So that they written different things on there. That's also a lot of different ones of them. Here also different kind of weather conditions and lane alteration. Sometimes, most of them, of course, is partially blocked. Some are fully blocked. So then others have lane shift, and some of them is none because some might be construction. You can still drive through that, like. And then here, a couple more cities, and this is just showing the test and train sample for those who do machine learning, computer vision, so that they are sort of equally distributed, but not right next to each other, because if then sometimes right next to each other, they look similar enough that they're not different. So, that's this. Okay. Now, how did we collect this? Because one big problem is that they're so rare, right? And we sort of bootstrapped. So how can you, so we try to use computer vision, find the scenes, but then once we find them, we train some more, then get a better model, and can find more, and so on, right? So I like new scenes has cones in it, so we can use that. And then we took like a little over 2,000 images in Pittsburgh. And we trained a cone detector on that. And then we can use that to mine images from large data sets. And we have two large data sets. One is the robotics data set, that's it's a public data set. It has from the whole cities, all pictures from all roads with telling how bad the roads are, good how the roads are. And then we detected, and then we collected data with a bus, just driving like every day, and we collected it on that, and it has like 100 million images, and the other one has 45 million images. Way too many to go through one by one. Okay, so you go through that with a detector and use detect and our own detector, and you put in the very low confidence, so you get about 100,000 candidates, which is much less than the 100 million. So it's like it's a factor of 1,000. You'd still have to manually go them through these 100,000 manually, and you get about 5,000 images. And then we trained models on the combined data. I mean, we labeled it and then trained the model on all of that. And we also looked at other data sets like BTD 100K and Mapillary that has about 25,000 images to discover more results. So we found about 2,000 from rural areas and so on. So you see some examples there.
What years are you looking at?
Data from what years?
What years? Yeah.
A lot of the robotics data is from 2019. Bus data is from 2019 to 22. And BDD 100K is from 2017. Mapillary is also 2016, 2017. So those were the. We also, some of the rural areas were collected last year. So we had someone actually drive to Arizona and back, and then we used that data.
Wow.
Not just for this project.
Okay.
Yeah. They were okay. They were going for a wedding.
Okay. Okay. Dual purpose.
So we're still working on it. It's not, and we have a paper out with that, so we submitted it, waiting to hear back. So one thing one can do if one looks at the long tail, right, and you don't have open data sets which are already labeled, you can go to these foundational models, right, and they are meant to basically one shot or low shot, zero shot learning, meaning they were trained on a large vocabulary, and you can ask them any phrase, any word, right?
For the most part, they are trained on internet data. So most of these models were trained on all of the internet, essentially. So the hope is that the internet has work zones. That is their hope. So which we show is not true.
Well, they don't, but not enough, right? If you use a foundational model like that and ask them, okay, find me these objects which are well interested in, it very often fails. So here's incorrect label. And here's missed objects. So, and if you score it, so if you take those open foundational models, the score is only like 4 or 6, which is very low. And so this score goes up to 100. 100 is like perfect. So this is very low. If you use our trained data, train a detector with our data, you get much higher, like the AP50 to almost 60%. So that shows that those foundational models, they work in general, but in general they don't work very well for at least our data. Okay, so as I mentioned before, the other open data sets, which are widely used, they have very few work zones, so we want to try to discover them. So, and we discovered less than 1,000 in those two data sets. So again, if you use that channel vocabulary foundational model, in this we found 32 in mapillary, 125, but if you take our model, you find 511 or here 500. So that's much, another showing that it's much better. And here's a couple examples, but this is also interesting that ours discovers work zones in other continents, right? And sometimes, you know, like these yellow barriers, they look a little bit different than our usual orange barriers, but they still found it. So it's interesting that it can generalize a little bit at least, right, to other countries. That's good. We did also a little bit a study on how good does our detector channelize across geography. So, like the way they do work zones in San Francisco looks a little bit different than Pittsburgh. Like here's tubular, these are cones, this is tubular, and then others have these flat things, right? And so there's a large variation in work zones objects across regions. And so we did a little test. I think here's more. Okay, so so this vertical panel, it's a tubular markers. Here are barriers, and sometimes, I mean, they don't look like. Now we as humans recognize it immediately, but they look quite different, right? And work vehicles that's crazy. What the variety there is. And here we did a little test, and it's like, okay, if you train only on one city, how good are you? If you train on two cities, how good you are? And then so you see those two curves. Only if you train on all 18 cities, if you get this high recognition. And so there's still some challenge trying to generalize from one area to another area. This is another way to look at it. It's sort of a complementary way to look at things. You look instead of at all the objects, you look at individual objects, how good they are detected, and so just ordered in how good each individual object is detected. And we compare if it has been trained only on Pittsburgh data, then trained on Pittsburgh data and some unlabeled data, and then trained on Pittsburgh data and labeled data from other cities. So this the green last one here is sort of equivalent to the endpoint here, right? So, but this time across different objects. And you see some objects, even if it's just trained on Pittsburgh data, is getting pretty close here, right? That's pretty good. But others like bike lanes, it's Pittsburgh, only Pittsburgh is very bad. Might be because all the bike lanes here are put in later, right? And not originally, so that might be. So that also shows, you know, some it generalizes good, others it generalizes worse. Okay, so what I just mentioned is detecting single objects, right? So now the next step is, okay, so can we understand those things which we detect a little bit better? So these are work signs. So here's an example where we are actually reading the signs. The green one, that's the ground truth. So what we hope to read, and the pink is what is actually detected. And then this one, it's good. This one, it does not detect. It does not. It's not able to read. So this one here, no blown up. It reads the text correctly, and here it doesn't find it. So it is still a challenge. And here's another example. Here's a slow sign. Here's a slow sign, and it sees the one, not the other. But one thing one can do and improve that is combining what we did earlier with this, meaning if we first detect the signs and then cut it out, maybe you can blow it up a little bit, and then try to read it, that's much better. And that glass is a certain detector which can read text in the wild.
Is this really that manual? Like you have to do this, or is AI doing this, or
What,
like
the-
it's blowing up on the signs and
We can, well,
you do it? Can it be done kind of?
it automatically, yes.
It is,
So-
okay.
So yeah, we have our script basically which says, okay, take that image, detect objects,
Okay. So
and
it's not a human.
no, it's not a human. No.
There was a time there was a human doing that. I remember.
Yeah, no, but like
Okay.
in all the earlier you might sometimes seen those boxes, right?
Right.
So you just so here, like this one here, we still have the box. We still know there is a sign, but we're just not able to read it. So if we take this box and say, okay, we cut it out, we know where the box is, so we maybe make it a little bit bigger, and I say, okay, give me that thing.
But that's all being done automated. That's the
All
whole
automated,
process.
yeah.
Okay,
Yeah.
good. You say we, so that's why. The royal we.
I think, yeah, me in my machines.
Yeah, exactly.
Ideally, we would like glass to do it on its own, and it doesn't. So we wrote that code to do it.
Okay.
So we would ultimately like to develop a model that can do it on its own.
Right. Correctly.
Does that make sense?
Yes, I know there was a time you had to hire people
Yes.
to do this manually. And
Yeah,
so
yeah,
I was
yeah.
hoping you made progress, and you have. That's good.
Yeah, I mean, you would expect that anything which is trained, learning and so on, that it basically trains the best of all possibilities. But as long as you can do something like on top of it to make it better, it's not yet trained.
Got it. Thank you.
So it's a simple crop rescaling sign significantly improves the performance almost here. Yeah, it's really big difference there. Here's another example. This is where even if it's a large sign, it's sometimes difficult to read. Like again, blowing up here, you see there's some dirt here, right? So then it thinks, gets that letter on. Instead of keep right, keep bite. It might be. Now maybe you can do some post-processing and say, okay, that doesn't make sense. It's not a word. What is it closely related? So you can still might be able to do something there. But still, there might be dirt or there might be occluded or something like this, right? Okay, so next is analyzing the whole work zone, right? There are, again, there's these big models. It's foundation models or vision language foundation models, which are trained on a huge amount of data, right? I mean, millions and millions of pictures which are annotated. And so that would be like your first thing to do. And but again, work zones are rare, so they might not have been trained with those or not trained enough. So these are two examples. This here is the ground truth. Ground truth meaning is what a labeler our team,
An expert labeled it.
expert labeler.
Because actually getting these labeled is very difficult, because if you give it to a layperson, they do not know what it really means. So an expert labeled this.
Yeah. But it's still, even if, especially these things, if you would have two expert labelers, the text would not be identical, right?
That's true.
So, but that's how you have to deal with text. So if you just take one of these large language foundational models and ask it to describe this, you'll get a text like this. So it's like, how do you actually evaluate a text whether it's correct or not? So it's color coded here. So when it's green, that's correct. When it's red, it's wrong. And when it's blue, it's either redundant or like irrelevant, right? So, you see that here, and then this is fine-tuned, meaning we're using our data, and help fine-tune the model, and then so you get it a little bit different here. This is only one example, right? But if you score it over many examples. This is the rough score. Don't ask me about the details about this. But this is 9.4 and this is 48, so this is already much better. Now, what you can do in addition to that is like, hey, what if we not just give them the image, but we already detected stuff in there. So we kind of prod it a little bit and say, okay, we have cones in here and so on. So we tried that. So we grounded with an additional object context, right? So these are the same images, right? The same, this is the ground truth. This is the same which I showed earlier, just repeat it here. And then this one here, now this one is a very good example. Of course, we show a very good example where it got it all right? But it's still not perfect. Here's a score. It improved it somewhat. So, but it helps. So we can use the one to help get the other. So next, last one is driving through the zones. Okay, and you can do that reasoning in the camera view or in a bird's eye view. So here is the camera view. So it's like putting the path here in the camera, and here's the bird's eye view, right? Where well, for this you actually need like a map, right? You don't have all this information in the one image, but you're here, you get this first, and you can then start trying to reason. Okay, it has to be on the path somewhere, and can get to different places. And then here, this is the data. This data here is the same overlaid like with this here. And so you can use that to train your model on trying to predict. And then let's see. Okay, so here's, okay, yes, the way we are a little small deviation. It's like, how do you actually get those paths? Okay, so as I mentioned earlier, we have like these video sequences, right? Now we also have GPS with that, and so you can take that video sequence and you can put it through Colmap. That's a certain software which takes the one image, compares to the other, finds feature points, matches them, and makes a 3D reconstruction. So you see here, with this, out of this sequence, it makes one 3D reconstruction. So that's a point cloud. You see these little points here and points there. And then this red one here is where each of the camera was when the picture was taken. Right? So this sort of, it looks like now like a breadcrumbs right here, where the path. And then once you have that, you can take that and project it back into the image, and that's how you get the path. So here in this case, so you take this path, it's going to project it here, You can see it. So that's, luckily, we don't have to label that by hand. But we can do it automatically with this. And then here you can see, so the blue dots here, that's what we give as input for the prediction. The red dots, that's the ground truth, meaning that's the path that the vehicle will actually drive. And then this rainbow thing here, like with the yellow in the middle, and that's the prediction. And this different color means just like how likely it is to be at this place, right? So that the yellow is higher likelihood, and this number to the side is blue. And here in this case, it's you know, tracks it pretty well. Not always, of course, but some. You know, and sometimes, of course, these paths, they look weird because while it's driving, there's another car coming, so it has to go to the side, and there's no way you can predict that, right? That's why you have to have a lot of it to make a model, and then it's also why you can only have a, you know, a probability distribution, and not like one fixed path. So with this, we are able to show that we can do predict the past. And then also to mention, so we give it a picture. We also give it all the objects which we detect. Right. So if we detect a couple of cones, right, then it can take that as a cue that, oh, probably I'm going to drive through that. Right. So here a couple more examples. Again, the blue here, this is the input, right? The red is the ground truth, which then it turns out to actually drive, and then this light one is the prediction. So here, in this case, what it seems to be is it's like it looks at the car and follows the car in front. So see that there, and there, and there. So it's actually pretty smart. Just follow the car in front of you. Now, of course, with all the things, you never know actually what it's thinking. You can't ask it. But it looks like that, right? Now here's a place where it actually makes a mistake. Here, from here, it goes straight up into this. But in the next frames, it recovers and then sees, oh yeah, I'm taking a detour there. And goes along that. Okay, that's what I have to say about these things. So a quick short summary. So work zones are dangerous. It's one of the very dangerous places. Just detecting the work zones is not enough. You have to recognize the objects, observe all the minute details, analyze the whole scene, and then you can drive through that. And we have that ROADWork dataset, which helpfully is like one step further in helping to drive autonomously through those scenes. So, thank you very much.
I was wondering, who sets the standards for work zones, if there are standards?
Oh,
Like, would Philadelphia be different than Pittsburgh? Allegheny County be different than Butler?
Policy here?
Yeah. Well,
I mean, it is. I mean,
it's usually set by the state.
It's usually set by the
It's
state.
usually set by the state. And actually, there's something that we're involved in called the Smart Belt Coalition, which is connecting several state DOTs together. And we're actually looking at this issue of work zones, and also with the eventual idea that it'll work towards where we have more automated and eventually autonomous vehicles. So there's more of a connection, so you're not driving a car and then you have to change the car when you cross over into another state when you're driving from Pennsylvania to Ohio, for example. So it's typically set by the states, and then the state DOTs often do the work. But then it doesn't mean, but then you have cities that do their own, work zone, and they have their own issues so we're working with the Department of Mobility and Infrastructure here in Pittsburgh. So it's usually the state unless it sometimes isn't. How's that?
Well, like a lot of times, it seems like a separate company sets up the barriers and everything.
Yeah, they're contracted by
But
state.
are they licensed?
Absolutely. That is all absolutely. They can't do that without, and they will have, like you'll see, they have to have a license and they're insured and all of that because of liability and everything. Absolutely.
To add to that,
Did you want to add to that?
Yeah,
every state has their own handbook for how the work zone object should be. So that is what decides what everything should look like in terms of specification.
Yeah, I wanted to follow up with your question, if I could. AASHTO is the main organization that promotes guidelines and standards for signage and that sort of thing. I was wondering if you're interested in using your database for improving automated driving. It seems to me you could use it for trying to figure out where standards should be improved.
Absolutely.
It seems to me something like signs should be standardized.
Right.
And you have a lot of examples where they're not.
Yeah. And I mean, this is just a starting point, but you could imagine that you say, well, can we find out if there's any places where it seems like it's dangerous? So you could look at these paths, right, and see where are they like very crooked driving or.
Oh. Sorry. I'll go to the. Anybody have napkins to spare?
Okay. What was I to say? It might be possible to actually look at a data set like this and look at the paths, right? And see if there's some kind of correlation of unsafe driving with a certain set of the objects there. Now you want, I mean, the extreme cases is at the very beginning where they went right through the markers because they were apparently too far apart. But you could look at hard braking and things like this in work zones and see if there's some correlation there.
I have a question regarding the fine-tuning of Lava, because you showed us the option where you would include some kind of context during the pre-training phase. And how do you do it? How do you include the context during pre-training?
Okay, I can answer that. We directly just add it in the prompt. So we give it the box coordinates and the box category name. So like we say cone at this location, cone, whatever, PTC sign at this location and so on. So it's part of the input prompt. So we are asking it to describe the work zone, and in that we are saying, oh, we already detected these objects and here are the list of objects that we detected.
Well, if you have this information in the prompt, then first you have to have another pipeline that will come up with these coordinates. Otherwise, how do you have the coordinates?
Yeah, so the thing is, these Lava-like models, they are generally latency sensitive, so they take a lot of time to run. So generally, most of these cars are already running an object detector. So it is already detecting an object, so okay, detect these work zone objects too. So the idea is to interrupt it and use Lava sometimes, if that makes sense.
Okay, so first you have a detector, then the output you kind of use as a prompt, part of the prompt, and then you get the output from Lava. I see.
So a lot of these car companies, from what it seems, want to use some of these VLMs intermittently in these hard situations, and they do not want to call them all the time, because it is too expensive to run on the car.
So sorry, just one last follow-up. So you said that sometimes often we don't want to use VLMs, so then we just stop at the phase of detector, Objects.
Yes.
And what's the trick? I mean, what's the criteria to say, yes, we want in this case to use VLM?
There are many ways to do it. One is if you use the detector and it reliably finds all the objects, you can just set a threshold saying that, oh, I found so many workzone objects, so maybe I should call a VLM now. So that could be one way to do it. The other way to do it is you train it end to end to minimize number of accidents and learn the threshold, which is a more unsafe way to do it, where you keep waiting for the accident.
Okay, great, thanks.
So this is all based on computer vision, right? So you developing standards for what the work zone sign should look like, all that will help. But while doing all that, could you also see a role for communications?
Absolutely.
Connected vehicles, and could somebody who is doing construction, can they set up a pop-up message through communications to alert these systems? And the two can play together too, they don't have to be.
Yeah, I mean, absolutely. I mean, I often say like this, for the awareness of the vehicle, everything around, you can have maps, you can have computer vision or, like laser scanners or something, and so perception from the vehicle itself, and communication, right? So you might be able to communicate with other vehicles, you might be able to communicate with a traffic light, and or with
Or even the work zones, they.
the work zones,
they
yeah.
just
That would
pop
be
up something right there.
Yeah, it might be that, in the future, they will put up something there and it says, here's a work zone, it starts here, it ends here. These are the traffic rules which have changed. Now you can drive on the berm or avoid the traffic. That would be probably much safer.
Much easier probably.
Much
than
easier, yeah.
trying-
No, I mean, also in general infrastructure, meaning like all these codes and so on have been put up there for humans to read, right? And it's, and the normal human is, can understand it, but several examples I showed you, if you think about it, it's actually difficult to understand, right? So, and with autonomous driving, there should actually be no error, right? There should be never any doubt what's there, what the rule is, and what exactly it means. So to have some fixed rules which we communicated through, that would be much better.
You see, is there any efforts like that going on?
Actually, yes, and I know that we had a Future of Transportation Summit at USDOT headquarters where we invited all the university transportation centers across the country, so there were 40 of them, right, including us here, and all the universities that were part of that. And I can't remember the university, but they had a demo where they were showing something like that.
Oh.
So that there was, so there's a couple of universities that are doing work in that area, but that synthesis of what you're talking about, I'm not aware. It's classic, I'm seeing things in silos.
But that's how they are usually developed, but
Right.
the opportunity is to bring them together.
The opportunities to bring them together, and then the only thing I get concerned about is like how much hardware how many sensors do you need to put everywhere, and that's not sustainable either. So it's more, can you use the software as opposed to putting some sort of sensor or a tag on each piece of construction work zone? That's not tenable, right?
Yeah, my vision was that whoever is in charge of that construction zone, I don't know, the supervisor or somebody, would have one transmitter
Okay.
transmitting to all the cars that are.
One makes sense,
Yeah.
but on every,
Not-
I've seen
not
them where
one
they
on
have them
every
like
equipment.
every worker on their
No.
vest. And then you gotta, keep
Well-
track of all that and all that.
I always say the big question is how much are we willing to pay to save lives?
Yeah.
And if you take the example of mining, a lot of mines are automated, and they do have, everybody has their, I mean, I don't know all the details, but everything has their and they basically get it to zero fatalities, right? Because they strictly enforce it and everybody has it, and no more of these big trucks driving over those small cars because they couldn't see that.
Especially construction workers, if they're wearing something
Right.
that puts a, basically a, I guess, shield-like thing around them.
Yeah.
No vehicle can come into
That would
the
be,
shield.
that would be really cool. Yeah, 900 people die in work zones every year, and there are another almost 40,000 injuries.
Yeah.
In work zones, in the US, just the US. And then there's 44,000 people that die because of transportation deaths. So that's a lot of people.
I have a question on that number. When you say that amount of people die, do you mean people who work, like construction workers?
Yeah, I've just Googled it.
When I say 40,000 people die every year, that's all traffic in the United
Right.
States.
It's actually higher than that, it's closer to 44,000.
I'm just curious.
I'm behind the time. It
Yeah.
was
Yeah, I'm
But
just
it-
curious the ratio between people in the construction zone versus people in the car outside of the construction zone and then they go in.
Yeah, I don't know. That might be.
I have the number here, it's 891 people died in work zones.
Oh, okay, so it's people who are already in.
They are construction workers that die.
Yeah, these are people who are working,
Right, okay.
and that's when they say, slow down, my daddy's working here. Like, that's very
Yeah, Double
real.
the fines
Like,
and
really
all this.
And this
Don't
is
speed
every
in a
year.
work zone.
This is every year, by the way.
Yeah, oh yeah, in the US, just the US. So it's very real.
I think worldwide it's 1 million. Okay, in all
That
transportation.
number includes fatalities from vehicles running into fixed objects and that sort of
Yeah.
thing, in addition to workers.
Yeah,
Might be, okay, but it's still, it's lots. Way too many.
way too many.
I have two questions. I think you mentioned you could use, I forgot what's the name of the software, but you can translate the 2D image into and reconstruct the 3D representation of it.
Yeah, Coleman?
Yeah, and I was just wondering, because I know a lot of autonomous vehicle solutions right now are looking to use a mix of sensors, radar, LiDAR. So I would imagine they're already doing like a point cloud of 3D representation of what they're seeing. Does this take account of like the different types of sensing information?
Well,
'Cause-
it's just for the data set which we have here has only videos and GPS. So it does not have the laser scanner.
right. So and then kind
No.
of wondering how do you kind of generalize or like make it compatible with the other.
Well, in this case, we don't really have to. We only did this to get the path, so that we can get this path, so we can label these images with the path that the vehicles actually drove.
So just to add, I think what you're asking is how do you combine radar and LiDAR and cameras together? Is that what you're asking?
Is that part of the consideration or future work maybe?
So we don't have that data. We don't have LiDARs or radars in this data, so we can't do that. But there are people who do that. So that is
And there's-
that's an active problem.
Yeah. I mean, most autonomous vehicles, I think the only ones which are not is Tesla, using LiDAR. And there are also data sets, but those data sets are very huge. Are there actually some people online which are asking questions?
There are people online, but you already answered the question that they asked. And somebody mentioned the MUTCD guidelines for work zones as well, saying that they offer guidelines, but that they often defer to engineering judgment for the particular area. But you answered the other question.
Okay, and is that for the whole United States, for the whole country?
I don't know.
MUTC, I think.
Yeah,
But that might be guidelines, not law,
I
right?
think that's right.
I mean, there's also international guidelines, right? Stop sign looks pretty much the same here and Europe. I think Europe it's all the same except that the Brits
So
drive on the
there's
left
a UN
side.
body which actually mandates a lot of the common signage, and most of the signs outside the US are standardized. Only the US does not have standard size.
They also don't have the metric system, so it's just one thing at a time, okay?
I'm just telling you the fact. That's not on me. Okay.
You showed at the beginning like the example on Fourth Avenue where like the signage is misplaced and could cause a lot of confusion. In your training data, have you noticed any particular examples like that where the sign or a traffic control device is misplaced that could cause confusion, and how do you deal with that?
Many such examples. I mean, a lot of times the signage is on some truck that is just driving because they are taking the signage away from a construction zone. So that's one example. A lot of the times because they are of course working right in these work zones, so they just keep the signage somewhere close to the work zone, even though that sign is not in use. So I can tell you. So this is not. Please don't quote me on this, but a lot of the self-driving companies have a lot of trouble identifying which signage is relevant and which is not.
So these probably require more like manual validation and like labeling and so on.
Yes. So what the hope is that you use the VLM, the visual language model, to figure out these cases. That this is not relevant.
I mean, I don't know if that's ever going to be possible to solve that problem with the required certainty, right? I mean, yes, you can use those foundational model, and they might have a good guess, but anything safety related has to be basically 100%, right? So I think at the end it can only be solved by having strict rules, and that it's just outlawed to put those things in places where it can be seen, but it's not meant.
A lot of times they're just lying on the ground. Like that is something that we see a lot, because I'm assuming the workers, want to place them somewhere else, so they just put them on the ground, assuming that humans would of course understand that they're irrelevant.
But I often compare like autonomous driving with robots in factories. If you look what the companies have to do if they use robots in factories, they often like in cages, so they're like completely separated. And if you want to ever go close to it, you have to have a key and you open a gate and that automatically shuts them down, and then you can do them. And that's how they get them to basically zero fatalities in these. And so you have to have infrastructure, you have strict rules, and you have supervision, and you have to enforcement and so on. And that's what you might have to do in traffic too, if you want to get to zero fatalities, right? So, but it's you have to train the workers to like not leave this sign out. You have to cover it up or put it away. That's my opinion.
We're at the tail end, so let's stay for speaker.
Thank you very much for sharing your love. And to all of the attendees, thank you for joining us. Today's presentation will be posted on the Safety 21 website What's Happening page, along with a link to the video of the session. For students who are interested in engaging in transportation topics, the Transportation Club on campus is a great way to plug into transportation topics with fellow transportation enthusiasts. Thank you for attending our Smart Safety Connection seminar. We hope you will be able to join us again for our next session. In the meantime, please feel free to contact us with any questions. Thank you.